Hello everyone, I'm James Jose Baclan, and today I'll be answering questions from part 1 and 2. And the question 1 is, so we all know that a generator transforms mechanical energy into electrical energy. So the illustration goes, so here, from mechanical power input, it goes to the armature, wherein this is where the conversion happens. And during the process, we cannot say that the 100% of the mechanical power input will be converted as the same as the input. For example, you have 100% mechanical power input. We cannot assure that the output of that will be also 100% electrical power input, because during the process you will have some losses of power, and that's what we call the iron, copper, and friction losses. We will have iron, copper, and friction losses during the process, and after that conversion you will have an output of electrical power. So that's the flow of the power of the DC generator. So question 2 is, so there are two methods to improve commutation. The first one is resistance commutation. Resistance commutation. And resistance commutation is done by replacing low resistance copper brushes by high resistance carbon brushes. And the next method is EMF commutation. And EMF commutation is done by neutralizing the reactant voltage by reversing the EMF in the short circulated coil, so that you will have a sparkless commutation. So question number 3 is, and that term refers to voltage regulation. Question number 4 is, so the 5 reasons why generators are connected in parallel are: so these are the 5 reasons why generators are connected in parallel. First is the power capacity, second is load control, third is maintenance, fourth is economic, and fifth is compliance. So power capacity and load management. So in the first place, why connect generators in parallel, wherein you can also use a single large generator? So the reason is that when generators are connected in parallel, it becomes a variable, meaning the input and the output in that connection has a certain range, or it's varying. You can select, or you can have a connection depending on the load, or depending on the need of the load. Where compared to a single large generator, the power is constant and you cannot really use its full capacity. For example, you have a load that only needs a power of 10 kilowatts, and your your large generator has a rating of 20 kilowatts. So that certain generator, that 20 kilowatt generator cannot use its full capacity because the load only needs a power of 10 kilowatts. Compared to having a parallel generator, you can connect a power connection that produces 10 kilowatts, so that you'll be able to produce and you'll be able to give the load the power it demands. And next is the maintenance and it's economic. So why it's economic, and it only needs a low maintenance. For example, that large generator gets malfunctioned or broken, and it costs a lot compared to having two parallel generators. And in that two generators connected in parallel, when one gets broken or malfunction, the other one can still produce power to the load, and you can only replace it rather than when that large generator gets malfunction or broken. So the next is compliance. It's in having a parallel generators, it complies to the electrical standards, safety and protection. Question number 5. So the requirements are the frequency and voltage. The frequency and the voltage of the two generators should have the same rating. And we should bear in mind that the old and the new generators could sometimes not have the same parts, like the engine, the size of it, the load sharing controls, and the alternators, and some other parts of that are not compatible, and it's hard to connect that or optimize the generators in order to produce the output that the power needs. Now for problem number 1, part 2, we have the given 230 volts bus load. We have the P rated, then the V rated, then the percentage voltage regulation for G1, then G2. For G1 it is 500 kilowatts, for G2 it is 600 kilowatts. Then they have the same volts, 250. Then 3% for G1, 4% for G2. Then a change in current, which is 600 amperes, and the current for both generators are equal. This is 2,4. Then we divide that into 2. Ig is equals to Ig2. This is equals to the IT over 2. So 2,4 over 2. This is equals to 1,200 amperes. Now, next thing we do is to find the delta I rated. To get that, we have this is for the first generator. So PR1 is equals to BR2. Then we have 500 kilowatts over 250 volts, and that's equals to 500 123 divided by 250. That's 2000. For the next generator, we have PR2 over VR2 is equals to 600 kilowatts over 250. Then we have 600 123 divided by 250. We have 2,400 amperes. Next is we find the delta I of the generator 1. We have the formula I rated 1 over the percentage of the voltage regulation 1 times the V rated 1, and that's equals to 2000. This one 2000 amperes over 3%. Then it's V rated 1, it's 250. Let's solve that. 2000 over 0.3 times 250. That's equals to 2000 divided by 0.03. It's 0.03. So that's 266.67. Now for the delta I2, we have I rated 2. This is 1 over percentage of the VR2 times voltage rated the second generator. That's 2400 amperes over 4% times 250. That's equals to, this is 2400, and this is 0.04. We have 240 delta V. Now next is we have the delta I1 is equals to delta I1 plus delta I2 is equals to the delta I, and that delta I is equals to 600 amperes from the given here. Now delta I1 is 266.67 delta V plus 240 delta V. We solve that. We have delta V is equals to 266.67 alpha x plus 240 alpha x equals 600. We have 1.184. Now we can get our new current for the generator 1 and generator 2, and that's I new is equals to IG1 plus delta I1, and that's equals to our RG1 is 1200 plus delta I. Our delta I is, where's our delta I? 266.67 delta V, which is 1.184. That's 1.184. Now we have our I new is equals to I new answer times 266.67 plus 12, that's 15.79 amperes. Now for this is for I new 1. I new 2, we have IG2 plus delta I2, that's also 1200 amperes plus 240 times 1.184. We have our I new 2 is 12 plus 240 times 1.184. Our I new 2 is 1484.16 amperes. So these are our new current for the generator 1 and generator 2. This one and this one. For question number 2, we have the given RA is equals to 0.1 ohms. RSC is 0.05 ohms. Then RSH is 120 ohms, and the power is 10,000 watts, and the volts is 246 volts. Now we need to draw the circuit of the given. This is the voltage load, RSH, RSE, RA. Then IA flows here, ISH here, IL is here. Now we have the ISH is equals to VL over RSH. This is VL over 120. And for IL, we have PL over VL, which is equals to 10,000 over VL. Then the total current, the IA is equals to the ISH plus IL. H plus IL, which is equals to PL over 120 plus 10,000 over VL. Now we get the voltage here. E is equals to IA times its resistances, which is RA plus RSE, plus the voltage here. We know that E is 246 volts and IA is here, which is VL over 120 plus 10,000 over VL times RA is 0.1 plus RS is 0.05 plus VL. Now 246 is equals to add this one, then distribute to this equation. Now that's 0.1 plus 0.05 divided by 120, so that's 1.25 times 10 to the negative 3, or that's 0.00125 VL plus 10,123 times 0.10, that's 1,500. 1,000. Okay. Over VL plus VL, multiply both sides by VL, that's 246. VL is equals to 0.00125 VL squared plus 15 cancel plus VL squared, this one. Now it's a quadratic equation. So let's arrange it. VL squared, then this one plus this one, so VL squared plus 0.00125 VL squared plus 15 minus 246 VL, so that's 1.00125 VL squared minus this is equals to 0 minus 246 VL plus 15 equals 0. So that's mod 5 3 1.00125. RB is negative 246, RC is 15. So we have the VL1 as 239.44 volts, and our VL2 is 6.26 volts. Then since VL2 is way too small, we use this VL1 as our voltage. Now for question number 3, for the part 2, we have the given our poles is equals to 4, our speed is 1500 rpm, and our Z is 48 slots. Then there are 4 elements per slot. Now our flux is 2.5 times 10 raised to 6 Maxwells, and we gotta convert this into Weber, and that's equals to 0.025 Weber. Then our formula is E is equals to P times the speed times our Z times our flux over 60 MP. Now E is equals to 4 times our speed 15, our Z is 48, 48 slots times there are 4 elements per slot, times our Weber equivalent of the given Maxwell over 60 times a duplex winding times a pole, which is 4. Let's solve that. Now we have 4 times 15 times 4 times 48 times 0.025 over 480, and that's 60 volts. Now for question number 4, we have the given 1000 rpm, you have 200 amperes of current and a 125 volts. Then our R is equals to 0.04 ohms. Then we have a V brush voltage drop of the brush, which is 2 volts. Now the circuit for that is this is our EG, this is our 0.04 ohms. The current passing through that is 200 amperes. The voltage load is 125 volts. That's the RL here, then the IL coming from there. Now let's find RL. So that's equals to VL over the current passing, which is 125 volts over 200 amperes, and that's equals to 125 divided by 200, that's 0.625 ohms. Now our EG is minus the voltage passing to that is 200 times 0.04 minus VL 125 volts minus the V brush, which is 2 volts, that's equals to 0. Now EG is equals to 200 times 0.04 plus 125 plus 2, so that's 135 volts. Now at the change of RPM, we have the ratio here, EG1 over EG2 is equals to the flux is constant over the speed 1 over speed 2, and that's EG1 is 135 volts over EG2 speed 1 is 1000, then a speed drop of 800, then we should have an EG2 of 108 volts. Now to find our IL2, we have the equation for, and that's equals to 108 volts, then minus the voltage drop of the brush, which is 2 volts, minus the voltage here, which is 0.04, times our new current, minus the voltage there, it's 0.625, times the new current IL2, that's equals to 0. Let's solve that. We have 108 minus 2 minus 0.04 times alpha x minus 0.625 times alpha x equals to 0. We have our new current is 159.398, or let's say 159.4 amperes. So that's our new current. Now for question number 5, we have the given of 500 RPM, our eddy losses 150, hysteresis loss is 250, and we need to find the constant of the both of that. We have PE is equals to A times the RPM squared. Now that's 150 is equals to A times 500 squared. Our A must be 150 over 500 squared, and that's 0.006. And for our hysteresis, we have B times the RPM 250 B, and that's 500. Our B should be 0.5. Now our P core 1 is PE plus PH, and that's 150 plus 250, that should be 400. Our PC2, after the 30% loss, we have, that's PC1 minus PC1 times 30%, and that should be 400 minus 400 times 0.3. We should have a value of 400 minus 400 times 0.3 times 0.3. we have 280 as our new PC2. Next is we find the value of our new speed, and to get that we have 280 times the constant of the eddy, the 0.006 times the new RPM plus 0.5 na constant times the nu. We should have a quadratic equation, and that's 280 minus 0.5 n minus 0.006 n squared. We should have an answer of 0.006.5 and minus 280. We should have why is this not correct? That's 0.006.5 then 280. Oops, why is this not correct? 0.006.5 minus 280, that's equals to, yeah, now I see. We have n1 383.51. this our n2 is negative 121684. Now the mistake I did is that this value is 0.006. That's 3 zeros. That's 3 zeros. Now since we can't have a negative speed, so let's take this one as our new RPM. Number 6, we have the given of 100 amperes, an RA of 0.02 ohms, an RF of 50 ohms, an RSE of 0.05 ohms, and a BHP of 38. Now let's construct the circuit. We have this is our VL, our RF, this is our RSE, armature current, then our RA passing here, IF, then our IL. Now let's find IF. IF is equals to VL over RF, and that's equals to 250 over 50. We have 5 amps. Now IA is equals to IL plus IF plus IL, and that's 100 amperes plus 5. We should have 105 amperes. Now our EG is minus BL minus the voltage passing here, that's IA times its resistances RA plus RSE. We should have equals to 0. We should have EG minus 100, I mean 250 volts minus IA. Our IA is 105 amperes here. Our IA times RA plus RS is 0.02 plus 0.05 ohms equals to 0. Our EG should be 250 plus 105 times 0.02 plus 0.05, and that's 257.35 volts. Now our PDEV is equals to EG times IA, which is 257.35 volts times 105 amperes, and that's equals to times 105 21.75 watts. Now to get our P stray, we have a BHP times 746. You convert that to watts is equals to our PDEV times the P stray. We should have P stray is equals to 88 times 746 divided by 2702.75. Oh, I see the problem. It's plus, then yeah, that's plus, then our BHP is 38. Our BHP is 38 times 746, so that it will be converted to watts, times PDEV of 27021.75 plus P stray. We should have P stray is equals to 38 times 746 minus 27021.75. We have an answer of 1326.25 watts.